Hello everyone, welcome once again to this lecture. This lecture is going to be focused on the software perspective of CFD analysis. So we're going to have a look at how CFD is implemented in the different software programs. So what we're expecting from you to have already gone through the basic fundamentals of CFD. So you should be familiar with the terminologies associated with CFD and a good working knowledge of computers and basically any software would do. And I guess if you're part of this online lectures, you are surely at that level. Nevertheless, to remind it, what you can expect from us is that you will be familiar with how the different CFD software codes work. We'll see what's the difference between a general purpose code and a domain specific code. So these are the different manifestations of CFD. So stay tuned. Just to give you an overview of the presentation, we'll have the CFD software terminologies, some of the terms which constantly will be used by people in the CFD community. We'll be introducing you to the same, and some steps in CFD and associated expectations from the different software programs, how the different software programs offer it to you. We'll see some examples and a bit more from the architecture point of view as well of the user interface, because that's how we communicate with the software. And we'll also see some resources from where you can get some more information on the software perspective of CFD analysis. Well, some of the terms which often we'll be using is something called the user interface, UI, that consists of the graphical user interface and the text user interface. Any software has this, so you'll also be able to see this in CFD. We'll also be getting acquainted with what are the programming source codes available where you can modify the codes or where you cannot modify. In some cases it's not possible to access the source code, but you can do some customization. So these are some of the other terms which you might come across. So that defines how the software program with which you can interact, how it has been made in a way that it can do the tasks that you ask it to do. So there is some code behind it. We'll also see some of the input and output file formats and basic setup of a CFD problem, which you can expect from any software. So the problem setup in terms of mathematical models, which are basically representation of what the physics speaks about. And the problem setup also includes often the numerical methods. So how the equations which you might have on a paper, on a sheet of paper, how they have to be solved using a computing device. And you'll also hear the term grid adaptation or grid adaptation. So this is how the grid is modified, the mesh which you give to the solver to solve your given equations. It gets modified to take into account some special gradients, special kind of flow features. We'll also hear this term robust. A software is robust or a software is accurate. Now these are two different terminologies. The robustness of a software defines whether the software does not crash or if it crashes or not. So if it does not crash, that's when you say that the software is robust. Now when I speak about crashing, it can be because of the user interface. So sometimes it might happen that it crashes on Windows, sometimes it may not crash on another operating system, or it may. So that's more about crashing at the level of the operating system or the GUI or the graphics user interface that may or may not crash. But sometimes it's also because the software is not able to do the task which you have given it. So it can be that you have not defined your problem very well, and owing to this the software is not able to proceed further, it gets stuck. So that's what we term as robustness of a software, a CFD software. When we're speaking about accuracy, we want the software to give us results which are making physical sense. So that's what that's when we define a software to be accurate, able to do an accurate modeling of a given physical problem. We also will hear this term coupling or interoperability with other software packages. So you have a given software package, how well it can be coupled together with another one, a third-party software. So that's what we term it as the coupling or the interoperability. This is another term you would often hear if you're dealing with CFD. Let's have a look at the software architecture of a general CFD code. So usually it has options to input or output files. We also have things to define the physical model, the physics-based model. So you have some certain physics like say flow, which is defined by the Navier-Stokes equation. So it has been mathematically modeled and that's available. So you should have provisions in a given software to give inputs, what kind of equations have to be solved, if there are some modifications to the equations, and the constraints to the equations. So that's the physics model. A software should also be able to ask the user what are the numerical schemes, how these equations which are defined in the physics are to be solved. So you have methods like finite volume, finite difference, finite element methods, some of the examples that I've mentioned, which can be used to solve these physics-based problems, and the numerical schemes define how they are to be solved. So it should ask such inputs from the user. Any given software also should have the provision to handle the data and finally make some real sense to the user. So for analysis, you should be able to handle the huge amount of data which is generated inside a given computational domain. You should be able to analyze it well. So it has to have some data handling and analysis features. That's called post-processing in some cases, or in other cases, as I'm going to speak about, how we can handle the data to export it or import it and make it understandable for another software. And finally, that's one feature which often people are looking for, that's customization. So we should be able to customize the given software in three terms. First of all, we can automate the process. We can minimize the user intervention. In other cases, we can add new features. No, that can be done using some user-defined functions or some subroutines. And the third feature of customization is about how you can operate it together with a third-party software. The first party is you, the second one is the software which you're using, and the third party is another code. It can be a structural code or with which you want to use the CFD simulation to do some analysis on the structure, or in some cases also optimization is something else which people are looking forward to nowadays in CFD as the hardware costs are getting reduced. So after having known the architecture, let's have a look at what are the features most of the CFD packages have to offer nowadays. So usually we are looking for any given software to be able to handle a variety of mesh sizes, mesh types and mesh sizes. So it should be able to handle mesh like a 2D mesh or a 3D mesh. This is the general expectation we have. Another expectation we have is that we should be able to at least model fluid flow and heat transfer in any complex geometry. Some of the features, how you can characterize a given software is also about the programming language in which it is written, because that's very helpful, especially if you're looking for customization. So we are looking for ANSYS Fluent, which is written in C programming language, CFX, which is written in Fortran 90, and we have star CCM+, which is another very popular commercial code, which is written in an object-oriented programming based language. Now this can be like C++ or even Java or C Sharp, .NET, but you can do some customization in star CCM+ using Java applets, but overall you can see this is the source code. This is the code in which the equations are getting solved. It can be that ultimately this whole procedure is being shown to you on the graphics through some other programming language. So for example, ANSYS uses Qt for designing its user interface, but that's just for the graphic user interface. But at the background, or in the behind the scenes as they would call it, ANSYS Fluent uses C and CFX uses Fortran 90. Any software should have a variety of physics to be included into the problem, so you should be able to handle multi-phase flows, cavitations, combustions, and different kinds of combustions. And you're also looking for accuracy of the physics. And as far as numerics is concerned, the numerical methods are concerned, we are looking for a software which can solve the problem without crashing. So that's about the robustness. We are looking for a software which ultimately gives us accurate results. So that's the accuracy part. And ultimately we want the solutions as quickly as possible. So that's fast. We are looking for a software which is fast, which can do our tasks in a well-structured manner, in a quick manner. Another important feature which people are nowadays looking for is how well we can use the software either as a standalone module, or if it can be integrated with some other packages, other programming software packages. So we have this kind of trade-off that we are looking for. We want to have the features of the software in a standalone mode, but at the same time we should be able to also integrate it with other packages. So this is another feature we are looking for. The integrated environment which ANSYS offers is the ANSYS Workbench, but there are a variety of other optimization software packages like the Mode Frontier or Radios, in which you can integrate some different software programs in an individual software programs can be integrated into their uh, large workbench environment. And additionally, we are also looking for any CFD software to be able to handle it either on your given desktop computer, or if you can do your work, let's say, from home. So you have a server which can be accessed from another computer. So that's what we call as remote simulation. And surely most of the packages today have to be able to handle huge um, cell counts. So in that case, we are looking for parallel processing. So a given computer alone cannot handle huge mesh sizes. So we have to have a lot of different computers which are coupled together, and we can perform some parallel processing. So that's another feature people are looking for nowadays in CFD software. And if that is too limited, we have a huge list here which shows some basic features which you can expect from any CFD software package. So it should be able to handle 2D or 3D mesh. It should be able to handle a variety of mesh types, and we should be able to do a steady state as well as an unsteady or transient flow simulation. And usually we are looking for incompressible and compressible flows. Some software packages are limited as far as compressible flows are concerned, but almost all of them can handle incompressible flows. ANSYS Fluent is not limited in this regard, by the way, which we are learning in this course. And we can also look at software packages to be able to handle a variety of viscous effects. So it can be an inviscid flow or a laminar, or if it is a turbulent flow, either be able to actually resolve the turbulence, which is quite hard, or else to use some turbulence models. And also heat transfer and conjugate heat transfer analysis coupled together with fluid flow analysis is what we are looking for in CFD software packages. Some additional, or so to say an advanced models are available. We should be able to handle a variety of material properties. Sometimes we are looking for multi-phase flows, not just a single phase, as well as a reacting flow. So that's a combustion which can also be included. We should be able to modify the equations, so we should be able to handle different volumetric sources. Nowadays, of course, a domain which is not stationary and it is deforming, it is getting modified, so a software should be able to handle dynamic meshing. And some additional heat transfer models like radiation effects. If you have multiple reference frames, instead of doing a complete unsteady moving mesh analysis, if we can do some multiple reference frame studies. So this is all just meant to reduce the problem complexity. So as you can see, there's a variety of features which are offered by the commercial codes nowadays. We are going to look at some open source solutions as well, but that's only going to be a part of the presentation. My main focus will be on understanding how we can use the packages which are available commercially with some price tag, how they can handle the problems of which are encountered by product designers. So these are the basic steps in CFD analysis. Whenever we are looking for defining a problem, we should be aware of what our goals are first of all. And once we have our goals ready, then we start with creating the geometry and meshing it. As you can see here, when it comes to meshing, there are a lot of solutions being offered by commercial packages like CATIA, or what was formerly known as Pro-E. Now we have, it's called Creo Elements Pro, and within ANSYS we have ANSYS Design Modeler, and Star CCM Plus, for example, has its own inbuilt star design which has been integrated into the Star CCM Plus. So there are a variety of options available for um, creating geometry. So that's CAD systems. Once we have the geometry ready, we need to create the mesh. which is the discretized form of the geometry in which the equations have to be solved. So that's called the pre-processing step in CFD. So it may sometimes involve a lot of data losses when you're shifting from a CAD package to CFD. So you might have to do some cleanup, that is to remove repetitive surfaces or to remove some problems with holes. So most of the packages nowadays like ICEM, CFD, TGrid, ANSA, which is very popular, and Star CCM Plus has its own wrapper technology, which has been included also into ANSYS products of ICEM, CFD, and TGrid. So these are features by which you can make your geometry available for the solver to solve the problem, to solve the CFD problem. So in that case, once we take that discretized geometry from this step into the solver, that's where we set up the physical models. We set up what is the physics. We try to explain to the solver, okay, in which way the equations have to be solved, and we finally start having a solution to our problem. Once we have the results, we try to save it, we try to examine the results. That's when we say we are doing some post-processing. So this step can be performed in Fluent CFX or Star CCM Plus. CFX and Fluent have a combined post-processing tool called CFD Post, which is available within the ANSYS Workbench environment, but it requires an additional license. And once we are done with the results, once we analyze the results, we are in a position to predict whether we should change the problem, whether we should change the geometry, whether we should make some modifications to the problem, so that we can have an accurate prediction of our CFD simulation.